Hello everyone, today we will discuss support vector regressor model, and we want to compare the performance of the model against different kernels, for example linear kernel or polynomial kernel or RBF kernel. So let's start. By the way, I'm using inbuilt data set. So let's import that data, import load diabetes. After that we can say Scikit-Learn dot support vector machine, import support vector regressor, and from Scikit-Learn dot model selection we can import train test split. That will be used for splitting the data into training and testing. We also need Scikit-Learn dot matrix, and I'm going to evaluate the models using R2 score only, and we also need standard scalar, and of course we need panda as PD. So now we are ready for the data. So we can say load diabetes, and then we can define the data frame. We can define the data frame, data dot data, comma, columns equal data dot feature names. Okay, and after that PD dot data frame, data dot data, columns equal to data dot feature name. Okay, it's saying that feature name is not, maybe it's features name, or maybe feature names. Yeah, that's good. Then after that it doesn't include the target column, so separately we need to write down target column equals data dot target, and I think now it's ready, right? Now we have data frame. So if we want to see all the columns, size of the data 441, column names, age, sex, BMI, blood pressure, etc., and the last variable name is the target, that we will use for Y. Okay, if you want to see the correlation, so you can see the correlation matrix as well. So target has correlation of, I think that's a good correlation with the all features of the data. So now we are ready. I can define x equals data frame and drop the target for the reason because target is not included in x, and for the y we should have only target. After x and y we can split the data like x train, x test, y train and y test, y train, y test. And use the same train test function, train test split, and inside the bracket would be x, y, size of the test data could be 20%, 15%, and random state equals 42. Everything good. So we separated the data into training and testing set. Now in support vector regressor model, we need to scale the data. So first of all, I'm defining a variable scalar, and then scalar dot fit transform x, and the test is also been scaled. So if we want, we can also scale the y data as well, but I think it's not needed here unless the range of values in the y is problematic. Okay, now we are ready, everything good. Now we are ready to define the model. First of all, for the linear kernel, I'm going to name it model linear kernel like this, right? And then fit it using the train x and y train. I am using here linear kernel, right? Good. After that, now we are ready for the y predicted for the linear equal to linear kernel model dot predict x test. It will predict y value corresponding to x test. Everything good. So it means now we are ready for R2 score. R2 score y test, y predict. Predict is PRED. Actually, predict linear is the name of the variable. Great. And now we can print the value of R2 for linear kernel, and here we can write R2. Okay, it is giving 44.5%, not very high, but average value. Of course, we didn't tune the model and we didn't do too much pre-processing, and the size of the data is also small, so that's fine. And we are comparing different kernels here. That's the purpose for today's lecture. Okay, the second one was use polynomial kernel. So I'm defining the model again with the polynomial. So support vector regressor with polynomial, polynomial, and then fit the model. Great. Again we are finding y predict with polynomial. Model is polynomial. Predict x test. Is that okay? Great. And now I can find R2 for polynomial, R2 score with y test, y predict polynomial. Is that correct? Looks good. Okay, and now we can print R2 for polynomial kernel. Like this, and it is giving me 28.24 or 25%, which is way lower than linear kernel. So if we compare linear kernel to the polynomial kernel, linear kernel is performing better. One more kernel, redefine the model for RBF. Support vector regressor, kernel equals RBF, and now you can fit the model using RBF, right? We want to see how the model perform against different kernels. And now you can find, let me move the screen a little up, and now we can find the y predict RBF. So we can say model RBF dot predict x test, and now we can find R2 for RBF, which is equal to R2 score y test and y predict RBF. That's perfect, right? And now we can print R2 value for RBF kernel. RBF is radial basis function, that is good for the non-linear relationships. So let's see how the model perform against RBF. Okay, so it is only 18.22%. So what is the conclusion then? For this data set, diabetes, linear kernel performs best, or we can say most of the data in this data set has linear relationship with the target variable. So if this is the data, we will use linear kernel, right? So we can see how the model performance varies when we change the kernel, right? First of all, for linear, we got 44%, 44.5%, and then for the polynomial, only 28%, and then for the RBF, 18.2%. So I think that's enough for today. Thank you very much. See you next time.